We are finishing chapter 23 by doing hypothesis testing, but again, now we're just looking at means instead of proportions. We're going to use that same trip hammer problem, the one with the speeding cars, and we're going to walk through the steps just like we did with confidence intervals. So when you're doing sample means, just like proportions, the first thing you need to do is state your hypotheses. So there's two of them. You have your null hypothesis. Now, we are not doing P anymore because those are proportions. The symbol that we use now is mu, which is your mean. So it's what is the hypothesized mean that is for the population. Then your alternative is the same thing. It's either going to be less than the hypothesized value, greater than, or not equal to. So let's talk about that trip hammer problem. So we know that the posted speed limit was 30. So obviously you're assuming that the cars are going 30. So our null hypothesis is going to be that the average speed limit should be 30. But all those residents kept saying that these vehicles are exceeding the speed limit. So exceed means bigger than the speed limit. So the alternative hypothesis is going to be that mu is bigger than 30. So similar concept to what we've done in the past. Next piece of the puzzle. Check our conditions. Well, conditions for these, there's only two. It has to be random and it has to be 10%. So, was it random, the cars that were on the road? Yes, it's very safe to assume that those cars were random. We don't control who goes down that road. And our sample size was 31. If we tack on a 0, there is definitely at least 310 vehicles on the road. So our conditions are both met. The next part of hypothesis testing is your mechanics. So here's our steps for finding our mechanics. First, find your standard error, which we've done before. Then find your t value, similar to a z-score, but it's a t-score. You're going to take the sample mean, so that's the sample, minus the population mean, divided by the standard error. Now the p-value, we can't use our blue sheet because that's z-scores, and the pink sheet, doesn't work backwards like the blue sheet does. So to find your p-value, you don't have any option but to use a graphing calculator. So to do that, you do second vars. You're looking for option 6. It should say TCDF. Now, it's waiting for you to give it 3 different values. You need to give it the low and you need to give it a high. So that's going to depend, these two right here are going to depend on your shading. And then the degrees of freedom, remember, is always n minus 1. So we're going to be drawing pictures similar to what we did with z-scores, but we can't use the pink sheet like we did the blue sheet. So let's run our mechanics. So we need the standard error. So if you go back to, in your packet, turn all the way back to the second page where we found S. Because we need S. That was 4.04. And we're dividing it by the square root of n. And if you remember, there were 31 speeding vehicles. And so our standard error, and it hasn't changed from the first time we found it, is 0.73. So now we have to find our t-score. So the sample mean, also from that second page in your packet, came out to be 30.32. Our proposed speed limit is 30 miles an hour divided by 0.73. And I end up with 2 digits, 0.44. So if we think about a picture, because we got to know how it's shaded in order to use our calculator. 0's in the middle, 0.44 is over here. Our alternative hypothesis was a greater than problem because we want to know if the speeds were exceeding the posted speed limit. So we are shading to the right. So now is when you're going to need a graphing calculator. So press second vars, go down to option 6. So you're looking at something TCDF that looks just like that. Now our low, if you look at our shading, our lowest value is 0.44. Our high, it goes all the way to the right, so we're going to use 99 for our high. And our degrees of freedom, remember we take n, which is 31, and we subtract 1, so we have 30. And if you hit enter, I get 0.3315. So this is our p-value that we're going to need in order to state our conclusion. So the first, just like the first time we did hypothesis testing, state our conclusion, and it's the exact same rules as before. We are going to reject the null hypothesis if our p-value is less than 0.05, and we're going to fail to reject our null hypothesis if our p-value is bigger than 0.05. So since p was equal to, what did we get, 0.3351 or 3315, that is most definitely bigger than 0.05. We fail to reject the null hypothesis. And that's the 4-step process. Same process we've been through before. So all we're going to do is look at 2 more examples, and then we're done. Researchers tested 150 farm-raised salmon for organic contaminants. Do you remember this problem? This was the Murex problem. They found the mean concentration of the carcinogenic insecticide Murex to be 0.0913 parts per million, with a standard deviation of 0.0495 parts per million. As a safety recommendation to recreational fishers, the Environmental Protection Agency, the EPA, their recommended screening value for Murex is 0.08. Are farmed salmon contaminated beyond the level permitted by the EPA? So the hypothesis, the null hypothesis, is that everything is good, it's meeting the EPA's level, so that means that mu is 0.08. The alternative is, are they contaminated beyond the level? So that means that they're going past that level, which means they're bigger than 0.08. So we only have 2 conditions to check. Are these salmon selected randomly? Which yes, they are. 10%, they selected 150. If we tack on a 0, there's definitely at least 1,500 salmon in the world. So our conditions are good. Run our mechanics. So if you remember, the first thing we have to find is our standard error, which is found by taking your standard deviation, which we were told was 0.0495, divided by the square root of n, which is 150. Round, and I get 0.004. Now we have to find our t-score. So our sample mean was 0.0913. That was from the word problem. Minus our population mean is 0.08. Divided by our standard error of 0.004 leaves us with a t-score of 2.83. Draw our picture. 0's in the middle, 2.83 is over here. Our alternative said that we were greater than, so we're shading to the right. So this is where you need to go through your calculator steps. So second VARs, and go down to option 6, and it puts up TCDF. TCDF. Our low, as you can see, is 2.83. We're shading to the right, so our high is 99. Our degrees of freedom, 150. Take away 1 is 149. And if you hit enter, you should get 0.0026. And so if you look at our rules, 0.05 is the cutoff. That is less than, so since P is equal to 0.0026, we are going to reject the null hypothesis. Alrighty, one more example. Bjork Larson was trying to decide whether to use a new racing wax for cross-country skis. He decided that the wax would be worth the price if he could average less than 55 seconds on a course he knew well. So he planned to test the wax by racing on the course 8 times. His 8 race times were, and they are listed there, I'm not going to read them to you. Should he buy the wax? So, what's our hypotheses? Our null hypothesis is that his average speed was 55 seconds, because that's what he wants 55 to be the most. The alternative would be that his average is less than 55 seconds, because he really wants to be less than 55. Let's check our conditions. Random. We have no control over his skiing times. He doesn't even really, so it's definitely random. 10%. How many ski runs did he take? It said 8. If we had a 0, if he's a professional skier, do you think he's skied at least 80 times? I would say that's safe to assume. So our conditions are good. Let's run our mechanics. So we first need to find our standard error. Well, before we can even find that, we need to find our basic data. So we're going to back up. You need to go to your calculator, and you need to press Stat, and you need to press Enter in order to edit, and you need to type those 8 times into your calculator. So go ahead and type those in. Now press Stat again, arrow over to Calc, option 1, and we're looking for X bar and SX. So I got 53.1 for X bar, and I got 7.03 for SX. So now we can continue. Now we can find our standard error. So we need SX, 7.03, divided by the square root of n, which was 8, and I end up with 2.49. Now we can find our t-score. So our average for the sample was 53.1, minus our average for the population was 55, divided by 2.49. And that leaves me with a t-score of negative 0.76. So 0's in the middle, negative 0.76 is over here. If you look back at our hypothesis, it was a less than problem, so we're shading to the left. All right, graphing calculators. Second VARs, option 6, it brings up TCDF. Our low this time, since it's shading left, is negative 99. Our high stops at negative 0.76. And our degrees of freedom, n is 8, take away 1 is 7. And if you hit enter, I get 0.2360. 0. So our conclusion, since P is 0.2360, what are we doing? We are failing to reject the null hypothesis. And that's it.